All right. So, welcome to this session, on to the short paper session, the very last session of the conference on visualization and non-photorealistic rendering. We have 4 very interesting papers in that session, very interesting talks that we are going to hear. I would ask you to post your questions either on Discord or on the YouTube channel so that we can have nice discussions on all the topics that we are going to hear today. Looking forward to that session. So then I would ask to the technician to start the first talk, which is on Deep Eyes full automatic enemy character colorization.
Hello everyone. Today I'm going to present our work titled Deep Eyes Free Automatic Anime Characterization with Painting of Details on Empty Papers. At first, I would talk our background. The colorization of illustrations is a very time-consuming process. So many automatic line drawing colorization methods based on deep learning have recently been proposed. However, previous methods cannot paint details on empty pupils like this. The result of these methods lack details such as in the pupils. In real-world paintings, most line drawings have empty pupils that artists must paint in. Here, we aim to support the colorization of illustrations in practical settings by colorizing empty pupils. We propose the system to paint the details in empty pupils during line drawing colorization, making it practical for illustration support. Our method can transfer pupil details from the reference image. I mean, pupil details are details of pupils in reference images such as in the middle figure. Next, I would introduce related works. Based on deep learning, some semi-automatic colorization for illustration has been proposed. There are 3 ways to input color hint. The left shows the scribble-based method. The middle figure shows the reference-based method. And the right figure shows natural language-based method. Scribble-based method enables colorization accurately by inputting color scribbles or dots in regions that users want to colorize, such as the middle figure. Reference-based method apply a reference image as an input to specify colors. Natural language-based method allows users to specify regions and colors using natural language, such as words of the middle figure. These methods cannot paint details in empty pupils. Here, we introduce some previous studies that can create details not included in an input image. Style transfer is a technique that transfers the style of a reference image to an input image. It can generate the details in the reference image. However, this method is unsuitable for coloring line drawings of characters. This image synthesis method applies textures to regions in an input line drawing. However, it is designed for repeated patterns, so this is unsuitable for regions with unique patterns, such as in pupils. Image compression by Guo et al. Can create semantic details not included in an input image. However, most such methods don't allow users to select the content for the target region. In contrast, our system allows users to specify textures using a reference image. I explain our method system in this section. This is our system overview. Our system mainly consists of two networks that are an I-position estimation network and a correlation network. We combine the correlation network with the I-position network to automatically and accurately colorize. These blue rectangle areas show datasets for our networks. In our method, a line drawing and a color reference image are given as input. Our method targets facial illustration. If the image size is 224 by 224 pixels. In the bottom row and the upper left, the I position of the input reference image and the input line drawing are predicted by the I position network. Then the reference image is rotated to correspond the angle of the input line drawing. Eye patches around the pupils are extracted from the rotated image to generate the hint image. A hint image is generated from the input reference image during colorization. Then the hint image and input images are given to the colorization network. Finally, the system outputs the colorized image. Our method uses two types of network, namely the I position estimation network and the colorization network. The I position estimation network estimates I positions of input image, except for the input and output layers. The network structure is based on ResNet 34. The input layer has one channel to input the grayscale line drawing. The output layer has four channels to output the x and y coordinates of the right and left eyes. The correlation network architecture is almost the same as those for the drafting stage. Unlike the drafting stage, reference image is transformed into color filters using a histogram model, and these color filters are input into the middle layer of the network. Our method creates dataset to train the I position estimation network and the correlation network. The I position network is trained using line drawings with and without pupil edges. We create a dataset of line drawings without pupil edges because it is difficult to collect large quantities of illustrations without pupil details. Line drawings that are extracted from color images has edges. So we create line drawings with pseudo-empty pupils by filling areas and eye positions in line drawings with white elves. We create the ground truth of eye positions by manually specifying the positions of the right and left eyes. The colorization network is given line drawing without people details as input. However, line drawing that is extracted by previous line drawing extraction method is with people details. If this network is trained with line drawings that the pupils have edges, this network can't paint details in empty pupils of line drawing. Therefore, this network is trained using pseudo-empty dataset. This network that is trained with this line drawings dataset can paint details in empty pupils. When creating a hint image, if the eye patches are in the original scale, the coloring results will include areas that are unpainted or colored beyond the edges when the eye size is different between the input line drawing and the color reference image. To minimize these artifacts, the height and width of the reference image are independently scaled in the range of 0.5 to 2 times, and then the eye patches with a size of 48 by 48 pixels are cut out around the eyes. The cropped right and left patches are randomly arranged in one of four combinations: left right, right left, left left, or right right. We train the colorization network with the hint images. We use different loss functions to train the eye position estimation network and the colorization network. The loss function of the eye position estimation network is the mean squared error. The loss functions of the colorization network are L1 loss and adversarial loss. These losses were weighted as the ratio of L1 loss to adversarial loss is 1 to 0.001. In this section, we show colorized image by our system, and our method compare previous method. Output image is our method result. Our system could colorize the input line drawing with color from the reference image and transfer people details from the reference image. The proposed method enables highly accurate colorization of the eyes, even when the left and right eye colors of the reference image are different. Our method is compared previous methods. Color hint is in the blue frame, and the colorization result is in the red frame. Previous style transfer method fails to transfer details in reference image. Previous automatic colorization methods using color scribbles or dots colorize line drawing, but these methods can't paint pupil details in empty pupils. In contrast, our method enables the painting of details on empty pupils. Our method is compared with previous method using color reference image. This method applies such as the colors in the reference image to the left, to such as the line drawing image to the upper left. Our method to the right shows higher reproducibility of reference colors than previous method to the second right, when coloring multiple input line drawings using one reference image, and previous methods can't paint people details in empty pupils, but our method can. Our correlation network is trained by dataset with pseudo-empty pupils. We can see the effect of pseudo-empty pupils from the comparison between results using pseudo-empty pupils or not. Without pseudo-empty pupils, the result lacks the pupil details like this. However, our method cannot accurately transfer details such as highlight and shadows of regions other than the eyes. In addition, our method sometimes unevenly colors an image. Even for the pupils, the proposed method occasionally does not transfer small details, such as those in the red frames. We propose a system that can colorize an illustration in a way that reflects the details in reference image pupils. Our method accurately colorize small areas of pupils by predicting eye positions. To enable the painting of details on empty pupils, edges around pupils are erased in the line drawing. Eyes can be colored with different colors and details, can be painted on empty pupils. These tasks are not possible using most existing methods. We would like to extend the proposed approach to other areas such as hair in future work. I'm not good at English, so it would be helpful if you could ask me questions in simple English. Thank you for listening.
So thank you, Kenta, for this very interesting presentation. I do not see questions on YouTube yet. Neska posted something. Also nice work from her. We have a question here on Discord, which I would like to announce here. The question is, have you ever made your model available to studios or artists to try it out?
No, I our method can't use a artist now, but I open. I will open our code and after after a conference.
So you didn't do any evaluation in studios or with artists yet?
No, I don't evaluate our localization result, but we evaluate this result by no artist.
Okay, thank you very much. I think that answers the question. If there are more questions, just post them. If not, I will continue with one of my questions that I have. One of them is, I was wondering, you had those training data sets that you used for training the networks. How many images were necessary to use for the training data? So what was the number of images that you had to use?
We use 170 30 million 70,000 to train correlation network, and about 2060 million million to train eye position estimation network.
Thank you very much. We don't have any more questions yet on the channels, but I will ask one more question from my side. Do you think it would be possible in the future that artists also include their own knowledge into the process, so that they can include their own artistic considerations into the process?
What's the process?
Because maybe they would like to adjust the results a little bit according to their needs. Do you think that would be possible?
I method they can't fix the result by user. So if user fix the result, our method need added other inputs.
Okay, so it's a fully automated process currently. Great. So we don't have any more questions on the channel. So if you would like to further discuss with Kenta, please do so on Discord. And for now, I would like to thank you very much for your talk again. And we will continue with the program now. Our next talk is going to be about interactive flat coloring of minimalistic neat sketches, and it's given by Amal. Oh no, no, I'm right in the program. Sorry, I have to shuffle 4 windows here, and I'm confused a little bit, but that was correct. So it's given by Amal, and I would like the technician to start the video now.
We introduce interactive flat coloring of minimalist neat sketches, a simple framework for coloring sketches with gaps. Coloring of line art has mainly 2 steps. Firstly, applying a flat coloring and then adding extra information like shading and lighting. A quick solution would be to use the well-known and straightforward flood fill algorithm. Though it is a simple and effective way to fill colors inside a closed boundary, unfortunately it fails if the sketch has some gaps. And these gaps may occur because of various reasons. As an error from the artist, where he forgets to close gaps, or as a professional gap to simulate the light reflecting off an object, or as an artistic style. There are a few existing tools to do the coloring of sketches with gaps. Though the tools range from optimizing an energy function, as in lazy brush, to a learning-based approach, as in paint chainer, the coloring process is not as simple as the flood fill algorithm, which we usually use in the bucket filling tool available in most of the painting software. It is mainly because the user needs to repaint the same region several times. As shown in recent works, the gap filling in sketches can also be posed as an application of the classic curve reconstruction problem. Unfortunately, that also does not give a satisfactory result. In this paper, we introduce a simple Delaunay triangulation based tool for aiding the users in coloring sketches with gaps, which we call as minimalist sketches. As shown in the image, we make use of the underlying Delaunay structure to segment the sketch and interactively merge them to generate the expected output. Initially, we generate a set of points from the given sketch by placing points at each pixel position and is used to compute a Delaunay triangulation. Extra points are inserted at the image corners to consider the background. The figure shows a sample image and its Delaunay triangulation. The next task is to identify possible edges connecting the gaps, which we call transition edges. To do that, we take all Delaunay edges whose circumcenters of its associated triangles lie on opposite sides of the edge under consideration. Once we find all the transition edges, we segment the sketch into different regions such that each region is bounded by sketch strokes and transition edges. Then we create a graph from the segmented sketch by taking each region as a vertex and edges connecting vertices whose corresponding regions share a transition edge. We assign the Euclidean edge length of the transition edge as the corresponding edge weight. The over-segmented sketch has to be merged interactively. To do that, first we define a color strength variable for each vertex and assign its value to -infinity. Whenever the user picks a color and clicks at a region, the region will be filled with that color and the corresponding vertex will be identified. Recursively, the color is spread to the regions corresponding to the adjacent vertices, if and only if its color strength value is less than the weight of the edge connecting them. Whenever the color gets spread to a region, all its triangles are colored appropriately and its corresponding color strength value is updated to the edge weight. To ensure that the color is spread through the largest gap first, we make use of a priority queue. So, whenever the user clicks at a region R1, the color is spread to region R2 through path 1 rather than path 2. This is how our tool works. As it can be seen, using our tool is as simple as bucket filling. These are a few sketches along with the result of coloring using our tool. Though we introduced a simple and effective tool, it has a few limitations. First of all, we connect the gaps using straight Delaunay edges, which might not always be sufficient. The figure shows input sketches along with the result of our coloring and the expected curve. Also, as it can be seen, segmentation sometimes misses minute features from human perception, like the connection between body and tail of the chameleon. To conclude this presentation, we introduced a simple and easy to use tool for coloring minimalist sketches. Also, it requires minimum effort. Currently, we are working on replacing the straight Delaunay edges using smooth curves and extending the work by incorporating methods to handle sketches with extra information like hatches. Thank you.
All right. So I think we are online again. Please just correct me if not. No, it's fine. So thank you, Amal, for this presentation. Thank you very much. Are there any questions to the talk of Amal? If yes, post them on in the YouTube chat or on Discord, please. And in the meanwhile, I will ask one of my questions that I have to your work, which is what would you say are really the main difference to the features that are available in image processing software already, like the GIMP feature or similar things?
Thank you, Johanna. So initially we had shown the result with GIMP, like that paper. That is the result of GIMP. So there what they are doing is They're identifying a set of regions initially, and the user can color each of these regions. So what we are telling is the artist won't be having that much freedom to give more colors or color the image according to his imagination.
Okay, very nice. And a second question I have is that did you also consider other triangulation approaches other than the Delaunay triangulation?
No, actually, this is based on curve reconstruction. Like there is a proven theorem that like it is like if the point set is sampled appropriately, the original shape will be subpart of the Delaunay triangulation. Neenamenta had proved that, so the entire idea is based on that.
Okay. And you already mentioned in your paper that one of the limitations is that you're limited to what the triangulation outputs. So that if there is some natural prolongation of the shapes, then this is not visible in the results.
Yes.
How would you tackle that in the future?
So currently we are working on giving, initially here we are finding some regions, right? So instead of that, we are trying to give the under control to the triangles itself. Like we are not going to find the regions. Instead of that, we are creating a big graph in which each triangle represents a vertex.
Very nice. Okay, and what do you think are the next steps in improving your algorithm apart from the prolongation of the regions?
Like if the image has some shading or hatches, using the current system, we have to paint inside each hatch strokes, which will be like cumbersome, it will be difficult. So what we want is, whenever we click, we want this color to spread inside hatches also. That's what we are doing currently.
Great. So then, if there are not more questions on the channels, I don't see anything in YouTube yet or on Discord. If you have any further questions, just post them afterwards. And then we will go on in our program and we will continue with the next talk, which is about pair correlation functions with free-form boundaries for distribution in painting and decomposition. And it's given by Baptiste. So we can start the video now.
Hello, my name is Baptiste Nicolet. I'm a master's student at École Polytechnique in France. And welcome to this virtual presentation in which I'll present a method for extracting accurate estimates of distributions from examples with arbitrary shapes. In this paper, we are interested in populating virtual worlds with distributions extracted from examples. For example, if we wanted to generate a realistic forest, then we could extract the distributions of trees, grass, rocks, and so on from images and then use those for synthesis, thus generating forests that could resemble one we could find in the real life. Now, there are a number of challenges when extracting data from examples. One of them is handling boundaries. To illustrate, if we wanted to extract the distribution of trees from this image, then we would need to take into account the fact that there is this river in the center, and there's a discontinuity in the distribution. Otherwise, the distribution we would extract from this image would not match the underlying distribution of trees, meaning that at the synthesis stage, we will generate a forest with a different distribution than the one we see here. So let's see first how distributions are usually described in our context. First method I'll introduce is Emilia et al. In 2015, in which each distribution is characterized as a density histogram. And these histograms can be computed pairwise in order to analyze the interactions between different distributions, such as here between trees and grass, or grass and rocks, and so on. Now, in this paper, it is assumed that all examples have rectangular boundaries and no discontinuities. So we could not use this method to analyze the image in the previous slide. Otherwise, the synthesis would be very poor quality. In recent works, a more popular choice of descriptor is the pair correlation function, or PCF. It's a function from particle physics that was introduced in graphics in 2012 by Estirelli and Gross. This is a function that for a given point expresses density as a function of distance to this point. And this can be used to describe a point in a point cloud, or when averaging it over the whole point cloud as a descriptor for the distribution itself. As you can see here on the right, some examples. These PCFs can also be discretized and used as a vector embedding of points or distributions in a feature space that we call pair correlation space. And then in this space, some algebraic operations are available, such as interpolation, clustering, PCA, and so on. In our context, a recent method that relies on PCFs is Ekormienoka et al. In 2019, in which they extended the definition of PCF to distributions of disks in order to properly account for the size that each object takes in an example. And they also, similarly to Emilia et al. In 2015, compute interclass PCFs in order to analyze the relationships between different distributions. However, they still rely on the assumption that the examples are rectangular and without discontinuities. Other methods simply don't handle boundary effects since they assume that the domain they consider is large enough to neglect this effect. This is going to be our focus here. We'll try to extract descriptors of distributions from examples with arbitrary boundaries, and our aim is that those descriptors are independent with regards to the boundary. So first, I'll introduce how we compute these improved PCFs, and then we'll see how it applies in some practical cases, such as in painting and then clustering. Our idea for computing boundary-independent descriptors is based on the strategy of Emilia et al. In 2015, in which they compute a weighting factor for each point and each distance to the point at which they compute the density. And this weighting factor is defined as the length of the circle divided by the length of the circle that lies inside the domain, here in blue, and thus accounting for the missing ridges in the distribution. So if we had an estimate of the boundary, we could use the same definition as here in order to scale our PCFs in a proper way. This is what we are going to do by first computing a Delaunay triangulation of the point cloud, and then pruning some edges using an edge filtering method in order to retrieve non-convex boundaries and inner boundaries. And we filter those edges using a local criterion. We iterate over all vertices in the triangulation and remove all outgoing edges that are more than t times longer than the shortest outgoing edge. And in our implementation, we found that a value of t of 3 works in most cases. And this gives us a result, as you can see on the right, where all the blue edges are the ones that we remove with our filter, and thus allowing us to retrieve this inner boundary here. And now that we have pruned our triangulation, extracting the boundary is straightforward. And then computing the weighting factor for a given point and a given distance to this point is as simple as computing the intersection between the circle and the boundary, and then computing the angular domains here in green that lie inside the boundary. And since the radius is cancelled out in the computation, our weighting factor is defined as 2 pi divided by the sum of these angular domains. In order to test this, we generated some distributions in a square domain and then removed some samples here in the center and here in the corners. And since in these 3 cases the underlying distribution is the same, we expect to extract the same descriptor for these 3 cases. Here on the left, what you can see is the PCFs that are extracted using square domain handling. As you can see, they are very different from one another, and with our method, they are very close to each other as expected. And this works well even if we use much less homogeneous distributions, such as in this case white noise. As you can see, our method still reaches a very robust estimate of the underlying distribution independently of the boundary. Now that we have seen how we can extract a distribution independently of the boundary, let's apply it to in painting. So starting from this exemplar with the missing region, we'll try to fill this one according to the PCF, to the distribution we extracted from the remaining points. And we do so by adding samples using a gradient descent-based method described in Ekorminoka et al. In 2019. And we do so either using the PCF computed with a square domain handling here in the center and with our method here on the right. As you can see, with our method, there is no distinction between the in-painted region and the remaining. But with the standard PCFs, this fails. Mostly because this PCF has learned that at some point there is a hole in the region because it did not because it is biased by this hole. So it added samples much closer to each other to keep this missing region in the exemplar. So if we wanted to take a more visual example, let's say we have a clearing in a forest and we want to replant it according to the distribution of trees in the rest of the forest. Using our method, we are able to extract the distribution of trees according to the trees in the remaining of the forest, and then compute the positions at which we need to add to plant some new trees. And then after a few years, as you can see, there is no clear distinction between where the clearing was and the rest of the forest anymore. Now let's see how our improved PCFs apply well to clustering tasks. In some cases, it may be interesting to separate unlabeled data into multiple classes, namely in order to analyze relationships between different classes, as I mentioned earlier. For example, here we have an input point cloud that represents flowers, where we have 1 point per flower center and then 1 point per petal. And we would like to extract this from this point cloud 2 classes, one for the flower centers and one for the petals. And we do so by computing the PCF of each point in the input dataset, and then applying two-means clustering in pair correlation space. And using our PCFs, as you can see, we retrieve very well the centers in orange and then the petals in blue. And then we can use previous methods in order to analyze the relationships between the two distributions for the synthesis. Now, since we do not apply a specific algorithm for clustering, our method does not improve performance in some cases, since we only change the embedding of each point in pair correlation space. As you can see here, our method raises similar performance as previous methods. This is expected, since in this case there is no boundary handling necessary for computing PCFs, and that means that our improved PCFs are as pertinent as previous ones, and we have a similar performance. Now, in some cases, it improves performance, such as here, where, as you can see, our method helps removing this boundary effect. And what happens here is that since with our edge filtering method, we remove some edges here at the separation between the two distributions, we will sort of emphasize the shift between those two distributions, and the points that are near it will have more different PCFs using our method, and thus allowing us to separate them more easily in pair correlation space. And this gives us this result here. And now, of course, in some cases, the performance is not that great with our PCFs, especially when distributions are not different enough from one another. And that means in PCF space, we cannot clearly separate them. And also in some cases, we may not know in advance in how many classes we want to separate our data into. This is not something that we change, since we simply apply k-means clustering with the chosen k. A very important thing to note here when trying to extract classes from an unlabeled dataset is that since the PCF depends on the points we consider for computing it, there is a huge ambiguity between the PCF we compute on the whole dataset and the PCF in one class. Let me illustrate. Here you can see the average PCF of the orange points, and here the average PCF of the blue points when computing on the whole unlabeled dataset. So these are the centroids used for the clustering task. And now that we have separated our data into two classes, we can recompute the PCFs of each point, this time only considering the points in the same class as the point we consider. And this, when averaging it, gives us these PCFs. So as you can see, these are very different from one another, and there is this big ambiguity between the two that is hard to resolve when using unlabeled data. But to conclude, in this paper, we have introduced an efficient method for handling arbitrary boundaries in examplers, leading to improved PCFs that are independent of the boundary and that have interesting applications in painting and clustering. However, it relies on a user-defined threshold for edge filtering that may be hard to tweak in some cases. Also, it leads to much higher computation time. And for the clustering task, there is this huge ambiguity between the PCFs we try to separate and the number of points we take into account for computing the PCF. In future works, we are interested in working further on this clustering issue and hopefully propose an automatic clustering approach, and then also extend this method to distributions in 3D and disk distributions. Thank you.
Thank you very much, Baptiste, for this very nice presentation. Are there any questions here from the audience, either in the YouTube chat or in the Discord? If not so far, then I will start with one of my questions, which is, what do you think other application areas could be for your algorithm? So you showed it for closing holes in forest or for reproducing petals. What else could you think on how this algorithm could be used?
Well, the inpainting could be applied in many different cases. I mean, either in the inpainting example I showed in with the clearing in a forest could be used in a more complex setting by, let's say, ecologists who want to replant forests that were destroyed or erased for different reasons. And then using previous methods, you could extract the distributions of all the many plants that contribute to the ecosystem, and then from this determine how to replant the forest. So because in reforestation, this is an issue that you have to really know how the ecosystem interacts, how all the plants interact, so that you can replant in a pertinent manner, and that will last long.
Mm-hmm. Thank you very much. There is a question from the audience, which I'm going to read out now. How much signal do you need to inpaint a large discontinuity?
How much signal? I'm not sure I understand the question. I'm sorry.
Maybe, Valentin, you can a little bit elaborate on the question. What do you mean with signal? Okay, while we wait for Valentin to maybe elaborate on that, I have another question. In the paper, you mentioned that you would like to improve the performance of your algorithm by also implementing it on the GPU. So how is the runtime of the algorithm currently, also compared to related work?
Currently, if we compare to the method we compare to, the square domain handling method, we have a factor of, for the computation of the PCF, I think we have a factor that is around 10 our method is approximately 10 times slower than the previous method, and this is mainly because the complexity of our method depends on the complexity of the boundary. So the more edges there are in the boundary, the longer it takes to run. And since we have to compute this for every point and every radius, this is pretty long. But we do all this in Python, so it could be easily improved by computing this in C, by implementing this in C++ and using parallel instructions first, and maybe even a GPU implementation. This is easily implementable in a parallel way.
Sounds good. Thank you very much. So Valentin rephrased the question. How long can the discontinuity be in comparison to the noise signal you have? He's further elaborating on, say, you have a few noise points in your image, but 80% of the image is blank. Can you still in-paint it?
I'm not sure it would. I can't really say. I can't really give you any figures as to how much empty space we can fill in with how few points. But we should have at least enough points to have some a good approximation of the distribution. In the example I showed with the missing region in the center, we have quite a big missing region already, but we didn't experiment further on the maximal size of the discontinuity region we could fill.
Would it be something for future work for you to test out how much blank space you can handle?
Yeah, it may be interesting, yes.
Okay. Thank you also, Valentin, for rephrasing that. Thank you very much. I hope that answered your question. Great. He says thanks. Yeah, then Baptiste, thank you very much again for your talk and for answering the questions. Thank you very much. We now go on to our last talk that we have in that session, which is organic narrative charts, and it's given by Fabian Bolte. We can start the video now.
Hello everyone, my name is Fabian and I'm a PhD candidate at the University of Bergen, and I'm presenting organic narrative charts, a work by my supervisor Stefan Bruckner and me. And I'm sure many of you have seen the movie narrative charts by Munro, where he displays characters, how they interact over time in movies, and we can see major plots of the movie over time. So this work has inspired many others, like the work by Ogawa and Ma, where they display how software developers contribute to software projects over time. But we can see that this is quite cluttered and unstructured representation. So Tanahashi and Ma took this further and applied or created an acyclic directed graph and apply a force layout to it to come up with a more structured and better readable storyline representation. Liu and others took this a little bit further, so they made a semi-automatic approach where they first apply an automatic layout to the storyline and then integrate interactions to order layers to straighten them and in general to improve the layout in a manual fashion. iStoryline is a work by Tang and others where they looked at how actual artists would create narrative charts, and they integrated many interactions to create digital representations that are much closer to what the artists want to achieve. So what we have been looking at is what Shelley's work, and he's an artist from New York, and he created what he calls diagrammatic paintings. So what this is that he shows how topics evolve over time. They are often art-related, and his paintings have a very visual appeal, and they're quite complex. So, for example, the streams that he's painting can change in size and shape. So this is different from what we've seen from previous work in the sense that they might be very unstructured, they are not, might not be as straight as the automatic layouts that were previously created. Also, he has splits and merges of streams. So a merge is when two streams become one, and the opposite of split is when one stream splits into multiple streams. Also, we have nesting of streams, which means that one stream can be drawn inside another stream, and this might have several depth layers. Yes. Also, there are a lot of labels in this painting, so we find labels outside of the streams, inside of the streams, and directly drawn on top of them. So we have several goals. We want to support all the visual elements of Ward Shelley's work in a digital representation. We also want to support artists in the creation of such diagrams, because they can be very complex and it can be difficult to come up with a layout that fits all the data that's in there. We also want to achieve a similar visual appeal to the hand-drawn paintings. Basically have like a somewhat organic layout, like wavy streams and an artistic style that is visually appealing. So in that sense, our goals are much closer to stream-based visualization, as we have seen by Kui and others, as well as Su and others, in text mining visualizations. So here we can see that there are streams nesting and merging and splitting, similar to what we want to achieve. But in our work, there are, for example, much more labels that we want to integrate into the layout. So our solution will build on a directed acyclic graph, similar to previous work. And we want to apply a force layout to create this kind of organic feeling and have much more control over how the layout looks like. We want to draw streams based on the node positions of the graph, apply an artistic style for image processing, and store the result as an SVG to allow artists to further refine their solutions. Here we can see that all the elements of Ward Shelley's work can be represented in a CSV format. And we will, based on this data, create a graph, which looks something like that. As we can see, there is, for a stream, we have the rectangular nodes. We show one node per time step of the stream, and they are connected via links. So this allows us to apply forces between the nodes. We also have round label nodes, and we have as many of them as we need to display the text on the visualization. We see that nodes can be nested, like the purple one inside the blue, and there are additional links that connect, for example, the orange links with the blue one, which creates a split here, as well as here a split of the purple nodes. So there are many forces that we can apply in a force layout. First of all, there are n-body forces. They push nodes away from each other. In order not to push them outside of the display screen, we have a centering force which pushes them into the center of the display. With a collision force, which makes sure that nodes are not overlapping each other, and attractive forces which allow us to, for example, display labels closer to the streams they belong to. There are also two restrictions, which is the border restriction that nodes don't go outside of the display screen, as well as a nesting restriction, which means that nodes that are nested inside other streams cannot be displayed outside of them. And here we see how, based on a graph drawing, we can draw streams that show our final results. So we can see the streams merging with each other. We can see labels outside of the streams and on top of them. So how we achieve this is based on the split streams library, which we created ourselves in a previous paper that will be presented at this year. And we can draw streams from nodes, we support splits and merges in the library, and we also support nested streams. So it has all the functionalities that we need to create our organic narrative charts. So here we can see how different forces can lead to different visual results. They can create very straight or very wavy forms based on how strong the forces between nodes are. So one question remains, and it is, how can we achieve the visual style that we've seen in some of our results? And how we do this is that we analyzed Ward Shelley's work, and we found that he's using a fixed stroke, an outer shadow, an inner shadow, and we want to achieve a similar application of color by creating some digital watercolor. And how we do this in image processing is to create a stroke, we start with the stream, we make it black, and we make it a little bit larger than before, and then we subtract the original stream from the black bigger one. So now we have created a stroke. For the outer shadow, we again start with the stream, make it black, make it a little bit larger, and we blur it. And by displaying it underneath the stream, we will see a shadow behind it. For an inner shadow, we start with the stream, we blur it first, and then we apply an arithmetic operation which will inverse the transparency. So everything that has been transparent first becomes red, everything that has been red becomes transparent. We make this black, and we have our inner shadow. For the watercolor, we start with what is called a fractal noise, and we will cut it into the shape of the original stream and apply color, and we already have some irregularities that look much closer to a hand-drawn painting. So if we combine all of these in the stream, what we will achieve is this kind of style. So when we compare this, we can already see that this is quite an improvement from what we previously had. Alright, so now let us consider two use case scenarios. In the first one, we have digital data available as we often have in the visualization domain. In that case, we can, from the data, create a graph, apply the force layout, draw the streams, and apply our visual style. In a case where we do not have digital data, we cannot follow this process. So let us look at this example. This is one of Ward Shelley's work, which is called Downtown Body, and it shows how art-related topics evolve over time. So if I am an artist and I imagine such a visualization, I want to create it, but it's very complex, it has a lot of elements. Also, if I'm a PhD student who has to recreate a digital copy of such a painting, I have the same problem. So what we did is that we came up with several interactions that make the process of creating the data easier. So here we can see our interface, and there's already one stream visible. In order to create a new stream, we have a drag and drop operation. Basically, we drag here, we move to another time, and what it will create is this stream. We also have something that we call a size slider. We can see it when we hover over our stream, and we can drag and drop it to increase the size of a stream. By that, we can adjust the size of a stream at every single time point. We can also create a link between two streams by dragging and dropping from one stream to the other. Also, by clicking on a stream, we can create a label. In this case, it's an outside label. There will be a pop-up window which allows you to enter text. Afterwards, you can change the type to be either inside or on top of the stream. So let us look at some of the results that we created. And this is our digital replication of Ward Shelley's Downtown Body. And when we compare it to the original, we can see that there are some similarities in the kind of style that we applied, that we are very happy about, but we also see that there are a lot of opportunities for improvement. So let us summarize. We managed to apply an artistic style to storyline visualization. So this can help to use your digital data and make it a little bit more visually appealing. We support the essential elements of Ward Shelley's work and support artists through interactions in an automatic layout to create their digital paintings. Our work is open source, and you can find it on GitHub under github.com/orca, where orca stands for organic chart. Of course, there are a lot of opportunities for the future. First off is the force layout, which has many parameters that are currently manually set. So they require some refinement to improve the layout that will be created in the end. And they also should be automated for the artists, or at least be in a semi-automatic fashion. So for example, we can imagine a slider which allows the artist to choose how wavy the streams should be, or how much empty space there should be, instead of having the direct force parameters to define. We also want to support images and visual embellishments that we have found in Botticelli's work, and fix some of the minor visual artifacts that we still have in our implementation. So with that, I want to thank my supervisor, Stefan Bruckner, and also the Research Council of Norway for funding our work. And thank you.
Thank you very much, Fabian, for this talk. Thank you very much also for this very interesting and inspiring work. Are there questions from the audience on the YouTube chat or on Discord? So there is one question, which is, how do you decide about the color of the links between two nodes? So is it based on the bigger node or is it random?
So we analyzed Botticelli's work, and what we found that in most of the cases is using, like when you have a link from one time step to the next, is often using the color of the node where it's starting. So from the left to right, it would always use the node to the left and the color of that stream.
Mm-hmm. Thank you very much. If you have more questions, please just post them on YouTube or on Discord. In the meanwhile, I would like to ask one of my questions I had, which is, you said that you would like to give artists a tool where they can create such stream layouts themselves and helps them to get an artistic layout and feeling about it. Do you think the force layout that you're using is hard to understand for them if they're using the tool?
So for one, we do not want to give them the chance to, we just want to make the process of creating such diagrams easier, because they are already able to create them, but there's a lot of data, and understanding where you should put which element and like adding them over time is very complex. So what we want to give them is some kind of a first layout. We agree that the first layout can be very hard to understand, especially with all the parameters that we have to set. And this is also why we, like one idea for future work is to create some parameters which are easier to understand, like make my streams more wavy or put labels closer to streams, which should be easier to understand for the users.
Mm-hmm. Thank you very much. One more question from my side is, do you think the artistic way of drawing the streams can also be applied to other visualizations, like a Sankey diagram or parallel coordinates or something similar?
Mm-hmm. So in theory, yes, we use the like our application is based on D3, for example. We are using the SVG filters that are available in the web. So you could easily take the exact same SVG filter from our application and apply to any existing visualization as well. You might want to adjust the parameters a little bit, because based on the height of the stream, for example, of the area you want to cover, you might want more shadow or less. You might want more detailed noise, or yes, but it would be applicable.
Mm-hmm. Great, thank you very much. So since there are no more questions from the audience so far, I would like to thank you for your talk again. Thank you very much.
Thank you.
And then some final words. So to all of you, to all the authors, thank you very much for your talks in that session. I think it was a very interesting combination of visualization approaches and rendering approaches. Thanks the audience for the discussions in the chats. And also thanks to the technicians that made it possible that everything was working so smoothly. Thank you very much, and enjoy the closing of the conference today.